In this video, we present RaLF, flow-based global and metric radar localization in LiDAR maps. Localization is pivotal for any autonomous robot, whether it operates in controlled environments such as factory floor or demonstrator environments such as roads and sidewalks. While camera and LiDAR-based approaches have been extensively investigated, they are affected by adverse illumination and weather conditions, such as snow and fog. Radar sensors, on the other hand, are intrinsically robust to both weather and illumination conditions, making them a promising alternative to cameras and LiDARs. In this paper, we propose RaLF, a novel deep neural network-based approach for localizing radar scans in a LiDAR map of the environment, by jointly learning to address both place recognition and metric localization. The place recognition task provides a global localization, but with inaccurate precision. Metric localization, on the other hand, estimates the accurate localization starting from an initial coarse position as input. RaLF consists of feature encoders, a place recognition head to extract global descriptors, and a metric localization head to estimate the 3 degrees of freedom pose of the query radar scan within the LiDAR map. The architecture of the two encoders, radar encoder and LiDAR encoder, is based on the feature encoder of RaLF. But different from the original encoder, RaLF employs a separate feature structure for each modality. The place recognition head has a twofold purpose. Firstly, it aggregates the feature maps from the feature extractor into a global descriptor. Secondly, it maps features from radar and LiDAR data into a shared embedding space. To train the plane recognition head, we use the well-known triplet technique, where triplets composed of anchor, positive and negative samples are selected online to compute the triplet loss. We reformulate the metric localization task as a flow estimation problem, where we aim at predicting pixel-level correspondences between the radar and the LiDAR samples using a raft-based metric localization head. Given the predicted radar-LiDAR pixel-wise matches, we estimate the 3 degrees of freedom relative transformation between the radar scan and the LiDAR map using the robust Rorschach estimator. During inference, we can combine the place recognition head and the metric localization head to accurately localize a radar scan within a LiDAR map of the environment without any prior information about its position. RaLF can perform global localization of a radar scan in a LiDAR map with a recall at 1 of 71% when tested in a different city and a different sensor setup than those used for training, demonstrating its high generalization ability. RaLF can align radar scans with LiDAR maps up to 6 degrees and 10 meters apart with a mean rotation error of 1.26 degrees and mean translation error of 1.07 and 1.03 meter for X and Y respectively. To foster future research, we release our code on the project website. Thank you for your attention.